I'm gonna like put 2 records. That's fun. Anyway, tell me. If you want to test this, what should we do? It's not about this, let's show about this question. You have a circuit and you would like to know whether this circuit is doing the right thing or the not. What are you gonna do? Exactly. Basically, you're gonna generate a truth table and you try to turn on the switches and see whether they're gonna give you output or not, right? That's basically what I wanted to hear from you guys. Okay. Same thing if you have a 1-bit full adder, right? So here is 1-bit full adder. So here is the box, full adder. Here is the CN. Here is the SI and carry out. And here is the 2 operand AI, BI. So in this case, somebody can help me with the table. So what are the input parameters we have in this table? Huh? What are my inputs now? AI, BI, CI. What is the output parameters?
Cout and SI.
Right? Okay, this table is covering how many states? 8. Yes. So you know the story, right? 2 power 0, 2 power 1, 2 power 2, right? You know how I calculate, right? Okay, 2 power 0, that means I flip 1 and 0 1 at a time. So 0, 1, 0, 1, 0, 1, 0, 1. 2 power 1, that means every 2 will be flipped. So that's why 0, 0, 1, 1, 0, 0, 1, 1. 2 power 2, that means 4. So every 4 I will flip. So 1, 2, 3, 4. Then you know 1, 2, 3, 4. You see how I flip? Fancy. Anyway. Here's M0, M1, M2, M3, M4, M5, M6, M7, right? How can I fill this SI and C out? Can you help me? SI in this case will be what? Somebody can tell me the values?
0.
0. And here's
1.
C out.
0.
0.
Okay. What about here?
1 0.
Okay, here.
0 1.
Okay, there.
1 0.
Okay.
0 1.
Okay.
And then 0 1.
Okay.
1 1.
Did you do correct? Is it correct? Yes, okay. Good. Now we will need what? Optimizer. We need to optimize the 2 circuits, right? So we need that what? K-map. You guys agree? 1, 2, 3. AI, BI, CI, 0, 1, 0, 0, 0, 1, 1, 1, 1. Right? Location 0, location 1, location 3, location 4, location 5, location 7, location 6. Now, this is gonna be for the SI. So in SI, M1 is equal 1, M2 is equal 1, M4 is equal 1, M7 is equal 1. And those are 0. Just like a checkboard, right? So if you guys remember, checkboard mean what? XOR. That means SI as a function of AI, BI, CI is equivalent to AI XORed with the BI XORed with the CI. Correct? Somebody can help me with the K-map for the C out.
0.001000101.
Wait. Oh, yeah. Okay, so what do you want to say? So M0 is equal what? 0, right? M1 is equal what? M2 is equal what? 0. Then M3 is equal 1. Then M4 is equal 0. Then M5, 6, 7, 1, right? 5, 6, 7. So in that case, how are we going to fix it? Tell me. So C out as a function of AI, BI, CI is equivalent one. Huh? How many terms this schema is covering for better
3.
optimization? Huh?
3, right?
Yes, you're right. 3. 1, 2, 3. And 3 of them will be all to each other. So this is group 1. This is group 2. This is group 3. So we can just write group 1 all with group 2, group 3. Right? That case would be what? Group 1. Somebody can tell me what group 1 would be. This is a group 1. Could be what?
A and CN.
A with C. Okay. Then group 2. What is going to be? Right. Group 3 would be what? Right? We finished? So if we build the circuit, it's going to be what? AI XORed. That would be XORed with CI and UCI and USS. Some, right? And then AI is PI and PI is CI, and that will be OR, right? Then that will be ORed with what? So I mean AI BI and BI CI still have AI CI, right? AI and then two will be ORed with this, and gonna be this here. You guys agree? Sounds good? Or anything wrong? Correct me if I'm wrong. Then we can define the critical path. You guys agree? Right? No.
Yeah.
Now I'm gonna switch to the screen with Vivado. Hopefully Vivado works. If not, I'm gonna next time I will put like a lightweight Vivado. Can you guys see my Vivado?
Yes.
Okay. So we're gonna click on the com.tst.v, the one I opened, right? The one I created. Oh my gosh, every time I say initializing, it's really gonna take forever. think it's gonna take forever, right? I think I have some issues with Java. I have to fix it. If I say add source, okay, and I say next, and I create, and I say here, you know, code add, and I say okay. I don't have to. Some issues in it. Let me share with you something else. More about it. I'll fix it next time. Anyway, now I'll share with you my screen again on the other side to show you how can we write this code for the circuit, okay? So again here, good driver. Extra one. Can you see my screen?
Yep.
Yes.
So there is a bunch of slides that we give it to you, but you know, we're gonna read it and then you know we can see how can we build the equivalency of the circuitry, okay? Better to apply every time that we build something, okay? So what is Verilog? Verilog is a language have been made by the Gate Design Automation and introduced in 1984, okay? And it started as the OVI, Open Verilog International. And then, you know, IEEE adopted in 1995 to be as a standard. Then they start revising the standard from time to time. That's why they already have a Verilog 2001, 2005, 2009, up to that, you know, 2009 they start what system. As I told you, system Verilog, it was just like, you know, for testing and verification more than just like writing register transfer logic, which is deployed on the chip. I mentioned that. So it's HDL, right? It's hardware description language. I mentioned to you in the beginning of the lecture that, you know, we're gonna learn some of the syntax for simulation and verification and some of them for synthesis, if you remember. Then we also mentioned the modeling. We have three different types of modeling, if you remember: behavior, structure, and data flow. And those are the differences between of them, as I mentioned before, but just to read it with you one more time. So behavior is describing the relation, like transfer function. How many of you heard about the control system? So you already have a block here. Okay, so if you already have a box here, right? And you already have a bunch of inputs and a bunch of output, right? If you study transfer function between input and output and you don't care that much about what is inside, that's called describing behavior. So that's basically the way that we're gonna use behavior modeling to build the circuit. A structure, that means you're gonna build blocks inside and you connect them to each other so they can be connected between the input and output. That's component level. Yeah, that will be on the modules on the week number 1. Okay, by the end of this lecture, I'm gonna post it. Then the third one is called data flow. In data flow, we allow the digital system to design in terms of function. So we're gonna use function to build the circuit more than just building components and gates. And the operators are used in this. They're gonna be those, and we're gonna discuss them in details. Let's go in the behavior. Here is the behavior. So I have a block, I have input, and I have output, right? I'm saying if there is signal called SHL, that means there is a button called SHL, high, that means equal 1, this form will happen. If not, make it equal 0. Just read this block with you. What is saying? After 5 nanoseconds, make this element inside the out equal 0. After that, puts an array. Every single array, the one before would be the one after 5 nanoseconds for each one. See? That's just an example. It doesn't mean that we're gonna make it, but I'm just giving you an example. Okay. For the structure, you build the blocks. Like you remember when I was building now the flip-flops, the full adder and half adder, you build them literally block by block. So for instance, if you would like to build 4-bit full adder, how are you gonna do? You're gonna build one full adder, SI, CI, AI, PI, C out, right? Then you cascade this to build 4-bit, like this. If you guys remember, rebel carry adder. How many of you remember rebel carry adder? Oh. Have you guys heard about it? Yeah. Oh, okay. I can tell you what is rebel carry adder. So I said I want 4-bit full adder. So that means, I need 4 units. So in that case, I have to have 1, 2, 3, 4. And full adder, full adder, full adder, full adder. S0, S1, S2, S3. CI, here is gonna be B0, A0. Here is gonna be B1, A1. Here is gonna be B2, A2. Here is gonna be B3, A3. Then the carry out here is gonna be carry in. Carry out here, carry in, carry out here, carry in, and this is the official carry out. What I built in front of you here is called RCA, which stands for what? Rebel carry. Have you seen this before?
Yes.
So the name is called rebel carrier. There is another one is called CLA. Carry, look, ahead, adder. I will discuss it with you another time. But at least RCA is the common one we use, right? So the one we built now, we can cascade it multiple times to build the bigger system, right? You guys agree? So we're gonna learn inside the Verilog how can we do it, which we call instantiation. So instantiate it. Okay. Now, more terminology to learn. I told you before RTL, right? Is a register transfer level, which is a type of a behavior modeling for the synthesis of the circuit that we are trying to build. So, you know, any code we write and we give it to the tool to synthesize is called synthesizable. And this is gonna be deployed on the chip on the board we have, not for simulation and verification purposes. Okay? And this is a kind of representation of the circuit using lookup table and flip-flops and so on. We can see this later. I'm gonna close this Vivado because I think it's crashed. I think I'll find a way to fix it. Anyway, so far so good for everybody. RTL synthesis is the way that, you know, the code you write, it will go to be transferred. So that's the process of transferring it into a gate level. And the gates for us is the lookup table and flip-flop on the, if you remember when I was building the chip, when I was generating the project, right? I opened something in front of you and I said, here is number of lookup table, here is number of flip-flops and whatever, right? This would be pretty much lookup table or flip-flop or DSPs or VRAMs. Okay? Sounds good? Example. You don't need to know what is written in the example, but just example, right? This is a code I wrote in the Verilog. This is a Verilog code written. Pretty much, it's telling you there is bunch of signals are input. Those signals will be used to build a key statement. It's choosing which one will be the output based on a selecting process. So if the select 00, the input A will be the output. If the select 01, input B will be the output. If the select is 10, input C will be the output. If the select is 11, input D will be the output. So if you go for RTL synthesis, inferred, so you will find out we are talking about what? A multiplex. That makes sense? Hello?
Yes.
Perfect. So if you look more into translation to RTL, that will be going in what? The combinational circuit. Gates of gates of gates of gates connected. See, gates of gates of gates of gates connected. So whatever I was describing to you when I was building the full adder and half adder, I was building the gate level implementation of the full adder and half adder. You guys agree? The tool will do this for you. So you will write the code, the tools will translate it to you. Then if there is a K-map need to be applied, it will optimize it to give you the final. So far so good? Hello?
Yes.
Super. I remember that I mentioned to you that we will have two different types of sets we're gonna learn from this course. Set will be focusing on the synthesis RTL, set will be on verification, which is simulation, right? So the tool, which is Vivado, is breaking into two parts. I write my code. There is embedded technology inside the tool. Then I will synthesize. Then I will build a netlist, which is a bunch of lookup table and flip-flops, and I will associate it with timing based on the critical paths that I was describing to you in the full adder and half adder example. Then we can send it for simulation to the simulation part, test bench. So the test bench will be also Verilog code, testing Verilog code, and running waveform simulation to see whether that, you know, the test is correct or not. And based on that, I can go in a final route and deploy on the chip. So Vivado is breaking into two species: RTL, test bench, and simulation. So in the journey of this course, we're gonna be learning set of syntax Verilog, but it's associated for the simulation, and another set of syntax associated for the part. So far so good. I'm just repeating what I said, right? Now, something to know before we close up. And we continue next time. So because still also you need to apply, you need to install Vivado. That's one of the missions you're gonna do this week, and also place the order for what? For the code, for the board. Sounds good? So if I want to write a Verilog code, if I want to write a Verilog code, what should I do? First of all, I will name the file with .v, and we already did that on Vivado. I saw it too, but later on Vivado became crazy. Then inside that file, we created .v. We have to be sure the beginning it will be called module. So we say module space, and then we put here the name. Then we close the file. The last line in the file will be called in module. Is it clear so far? So you start with module, then space, the name of the module, and you end with module. The name of the module, it's recommended to be the name of the file. So let's say that I call the file FA. And then this file is fa.v. So inside the FA file, I would say module space FA. And then end module. So far so good? No. So now there is pieces inside the module to create the circuit I'm looking for. So since I said the module is FA, that means I'm expecting this file to be what? Full out, right? So you have to declare ports. You have to declare what is the input and output. It's called port declaration. So you have to declare the port declarations. Then you have to describe what type of the ports and internal signals or internal network will be defined. So the type of the data will be used. Then you have to apply the syntax for the circuit functionality. And if you have something to add about timing, you can add. Okay? So good. Put in the consideration the following while you are doing this. What you gotta put into consideration? You begin the file with module. You end with what? End module. Be sure this language is a case sensitive. That means if you uppercase, it's different than lowercase. Be careful. Be sure all the keywords you are using and variable names are what? Lowercase. Be sure to make a readable file or module they call. Be sure to close every single line with semicolon. Be sure if you would like to place comment like in C, right? You're gonna make it like this. But this is for the single line. But what about multiple lines? You go here and you make a star and you go there and you're gonna make a star. So whatever in the middle will be commented out. Timing, I will leave it for now, so that will be advanced stage. So far, do you have any question? Any question?
Will you have these slides up on Canvas?
Yeah, every single thing. The video I made, it will be there. Everything will be there. Sounds good?
Yeah.
Now, I think it's better to stop because I'm sure that you are guys extremely tired.